what did we learn? We learned that there is a matrix that transforms the basis, and the transpose of the matrix can be used to transform the coordinates. Okay, we will do the same thing that we did before, but this time in n and n dimensional vector spaces. So what is the operator here? So let me write the name here. The name is, or the heading is, matrix representation of an operator. Now what do you mean by operator? So the operator is that one which took you from one basis to another basis. For example, when I write u prime is equal to some a u, here when I write such kind of equation, a acts as an operator. We don't know whether what kind of matrix A is, and after certain time, after doing some evaluation, we know what the matrix is. So whenever the equations are written in this way, without the matrix form, you say that there is an operator A that transforms the basis. We'll talk this way. So now let's do like this in a more mathematical way. Let instead of L, we have L. Let L is an operator or a map that takes you from a n-dimensional vector space to a m-dimensional vector space. So let L from Kn to Km be a linear map. Okay, then there exists a unique matrix A such that, so what the matrix does, when it acts on an element x which belongs to Kn, so let x belongs to Kn, then it gives you a vector in Km. So L of x belongs to Km. So if you don't understand this, then remember the example I did when I wrote a projection operator that took you from R3 to R2. Okay, and any element that belongs to R3 and say x belongs to R2, then the map, when it acts on a vector in R3, it gave you an element x. Okay, so now what we do here is so when I did this, I also made sure that L of x is equals ax. Okay, I had a little bit confusion with respect to notations. Let's see. So what is this A matrix? A matrix is a matrix that takes you from x to L of x. So it takes you from the coordinates x in Kn to the coordinates L of x in Km. Okay, so in the last class, I found the matrix F, which is transpose of F, which is 1 0 0 0 1 0. And what F transpose did, if you have an element in X and if you have an element in the other vector space, then F transpose will help you go from one coordinate to another. Let's see how I've written in the previous case. So here I have a vector in R3, and here I have a vector in R2, and F transpose takes you from a vector in R3 to R2. That is, it transforms the coordinates of the vector in R3 to the coordinates of the vector in R2. Okay, so this is F. Okay, so following the same line of argument, here I'm going to write the matrix which was our F transpose as A. That's it. That's the only difference. Okay. So any doubt with the notation? So A acts like F transpose that we did before, right? So I'm marking different notation, that's why there is a confusion. So okay, if there is no doubt, then let me proceed. So let me remove all this. And let's start the derivation. Okay, so if L is a map, and the map takes you from Kn to Km. So if there is a vector in Kn, then the L will take you to a vector in Km. So I can write this L of capital X as small x also, such that small x belongs to Km. Okay. Now consider that capital E1, E2, dot 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 En, they are a unit vectors, or you can say basis in Kn. So let they be basis set in Kn. Okay. And what is E1? E1 is a basis in Kn. For example, if I write E1 is a basis in R3, then how E1 is? E1 can be 1 0 0, and how E2 will be? E2 will be 0 1 0, and so on. So there will be up to E3 in R3, and if you have taken Kn, then there will be n bases. Okay, this is clear. So you have a set of bases in vector space Kn, and let small e1, small e2, dot 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 em be the basis vectors in Km. So as I said, if you have a space with R3, then the number of bases will be 3 bases. So the basis set will contain 3 elements. If you are in R2, then you need 2 bases, and so on. That's why there is n and there is m, and m is not equals to n. So if m is not equals to n, that means you're working with different vector spaces, and hence you're working with different set of basis vectors in both the vector spaces. What the map does? The map does the following. It takes you from Kn to Km. This is our map. What it means is that consider, so you have Kn, and in Kn we are going to have capital X, and in Km we are going to have small x. Okay, so in Kn all the elements will be denoted as capital X. In Km the elements will be denoted either by small x, or I can write L of capital X. Both are same thing. Okay, so now if you have a capital X belongs to Kn, then this X can be written as capital X1 E1, capital X2 E2 plus dot 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 plus capital Xn En. Okay, what does it mean? It means that X is a vector that belongs to Kn, and X can be written as a column vector with coordinates X1, X2 dot 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 Xn. Okay, that's the main idea. Now what I do, if I act the map L on X, it is equivalent to the fact that since the coordinates are just numbers, the map will not act on them, but the map will act on the basis. So this will become X2 L E2 plus dot 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 plus Xn L En. Okay, can you tell me L E1 belongs to which space? Alham? So if X belongs to K of N, then L of E1
It belongs to Km.
It belongs to Km. As I said, that L, if it acts on an element in Kn, then it will take you to an element in Km, but not necessarily you will end up with the basis. Now you would say that, okay, if L acts on a basis in Kn, so E1 was a basis vector that belongs to Kn. Now you would say that if L acts on E1 and it takes you to a vector in Km, does it mean I will end up with basis E1? Does it mean that this is same as this? Answer is no. When L acts on the basis vector, which is in Kn, it will not necessarily drop you to another basis vector in Km. It can drop you to any arbitrary vector. So let me write this. So if L E1 can be any vector in Km, and L E1 may not be a basis, may not be the basis in Km. So if L of E1 is not a basis, then this element which belongs to Km can be written as a linear combination of the basis in Km. So I can write L1 as linear combination of basis in Km, since L of E1 is a vector that belongs to Km. This is quite easy. Okay, so again, why are we doing with such a generalization? To give you a mathematical taste of how vector
I lost
are
your
taught
voice.
in some graduate or now we have, okay, I need 5 minutes from now. Okay, just wait. Just pause your recording for 5 minutes.
No.
Record now. Okay, So as I said that I can write L of E1, since it belongs to Km, I can expand it in terms of its basis in Km. Let the expansion coefficient be A11 E1 plus dot 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 plus A M1 E M. So what do you understand? This is how the L acts on E1 and takes you to any arbitrary vector in Km, and any vector in Km. So since it is a vector in Km, any vector in Km can be written as a linear combination of the bases in Km. Similarly, the same thing can be done with the basis E2. So maybe it will become A 2 1 E1 plus dot dot dot. No, A 1 2 1 E1, yes, and dot 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 plus A um, 1 2 3 4. Okay, it is A. Okay, this is quite confusing. So I'm going to use my own notations now. Let's try to understand the notation in our way. That would be nice. So let's use some logical basis set. So LE1 can be written as, say, A1 1 E1 plus A1 2 E2 plus dot 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 plus A1 M E M. So for E2 we have A2 1 E1 plus A2 2 E2 plus dot 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 plus A2 M E M. Okay, please both of you correct it if I get wrong somewhere. Similarly, L E, and we had the nth, so it will be A N 1 E1 plus A N 2 E2 plus dot 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 plus A N M E M. Okay, so now what do we have at hand? We have the basis. Okay, I'll come to this later on, but now let me just do it. So L of E1 is a vector in Km, and hence the coordinates of L of E1 are A11, A12, dot dot dot, A1M. That's it. Okay, now what we do? Now remember L of X, when L acted on an element X and X belonged to Kn, then L of X belongs to Km, and we wrote this as a linear combination in Km. In which way? I think there was X1. Let me see. So yeah, X1 E1. Okay, so there was X1 E1 plus X2 E2 plus X it is a vector in Km, so there should be Okay, maybe there is a mistake. So L of X,
It should be a small e.
just a minute. So X belongs to Kn, and we applied L on this. Okay. So we have not written Lx, but what we have done is the following. We took X, which belongs to Kn, and we wrote it in terms of x1 E1 plus dot plus xn En, because X belonged to Kn, and we acted upon the map on X, which means that each of this map will act on the basis states and now we can do the further calculation because we know what L of E1 is going to look like in terms of the basis E1, E2, Em. Why are we doing this? We are going to write all these in terms of basis Em, which is small E1, E2, Em, because we know that L of X must belong to K of M. Since we know that L of X must belong to K of N, so we should find a way to write L of X in terms of basis in Km, which is E1, small E2, Em. So that means L of E1, that is L of capital E1, must have a representation in terms of basis. So this is another way of saying it. Did you understand, or should I explain again? Let's do it again. So X belongs to K N. So hence I was able to write X in terms of some coordinate and the basis, and there was n basis, so it was like this. I said I defined L as a map that takes you from Kn to Km. That means any L of X must belong to Km, and L of X can be written as a linear combination of bases in Km. So I should be able to write all the L of X as a linear combination of bases in K of M, which in turn means that if I act the map L on X, it means that all the map will act on the basis here, because x1 to xn are just numbers. So this is what I get. But I know that this thing belongs to Km, so this gives me an idea that all these elements L1, L of capital E1, L of capital E2, and L of capital En should be expanded or can be expanded as a linear combination of bases in Km. Okay, so thus I can write L of X equals x1. Now what was L of E1? I know that L of E1 was A11, E1, A12, E2, A1M, En here, the first one. So let me write it. So it was A11 E1 plus A12 E2 plus plus A1N En. Please verify this. Let's see. 1 1 1 2 1 N 1 1 1 2 1 M. Sorry, M, because we are in M vector space. This will be M. Similarly, now you have the other stuff, and the last one is xn, and this one was a n1 e1 plus a n2 e2 plus dot 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 plus a n m e m. Okay, now bring all the bases e1. So what do you get? x1 a11 plus dot 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 plus xn a n1, and you see now I am writing L of x as a linear combination of bases e1, similarly e2, and similarly em. So this will become x1 a1m plus dot 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 plus xn a nm e to the power m. Please check if I'm correct or if I'm wrong. Okay, so em will have xn a nm and x1 a11 x1 a, yeah, it's correct. So what do you understand from here? You understand that since L of x belongs to k of m, that means L of x should be written as small x1 e1 plus small x2 e2 plus dot 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 plus small x m em. And now if you compare it with the above part, you see that small x1 is equals to capital X1 a11 plus dot 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 capital Xn an1. Similarly, other stuff can be written, and small x it will be m. Small xm can be written as capital X1 a1m plus dot 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 plus capital Xn a-n-m. So now you see that you got a matrix representation for the matrix A. Okay, remember from the very definition, what did we define? We already defined that there is a matrix A that takes you from x to L of x. By L of x, I mean small x. So if you look at this thing, you can easily find out what matrix represents A. Okay? Are you clear?
Yes.
So the matrix looks a bit weird. So it will have A11, AN1, A1M, ANM, but yeah, things are okay. So anyways, we have a matrix representation of A. That's the whole idea. Okay, it looked a little bit clumsy, a little bit difficult, but this is how most of the mathematics book, they do these derivations. They have n-dimensional space, m-dimensional space, and they will do the general derivation. But before doing this derivation, or whenever you see this derivation, you repeat this derivation in small spaces. For example, look at the derivation I did here. You see, this was almost the same derivation that I just did with m and n spaces. But since I did it in 2D, things was very clear. Okay, so whenever you face with such kind of derivation in any physics or mathematics text, what you do is you reduce the derivation to smaller dimensions, and intuition will be quite clear. Because if you look at these derivations in larger dimensions, then it looks a bit clumsy and a bit difficult, but actually the concept behind them are simple, not difficult. Is it clear? So this was not an important task at this point.
Yeah. So,
if you want, you can skip.
Yeah, I have one doubt here. Use transform from for k for one dimensions to another, that is from n dimensions to m dimensions, right? So
yes.
initially
Yes.
here we have R3 and then we reduce it to R2 in that example,
Yeah, you can compare
Yeah,
it
but
from R3
yeah,
to
but
R2.
in R3 we have our column matrices. Column matrix we first consider, and it reduced to another column matrix of R2, right? But can we do the same thing for some rectangular matrix or square matrix?
No, in this case, we already got a rectangular matrix. If you look at
Yeah,
this final matrix
yeah.
here,
After
it's a rectangular
transformations,
matrix because there is NM.
yeah. So this rectangular matrix is the matrix which transform from one dimensions to another dimensions, right?
More precisely, it takes you from coordinates of a vector in one dimension
Yeah.
to the coordinates of the vector in other dimensions.
Right? But now can we consider a matrix in one dimensions, I mean, which is a rectangular or a square matrix, and we reduce
Yes,
it
I'm
to
coming to that.
another
I'm coming to
dimensions?
that. Yes. I'm coming to that. I understood. It is the same question that Elham asked.
Okay.
Let's come to that. Okay. So now you can forget whatever I taught. If it was clumsy for you, forget it. Okay, do the derivation again to get a proper intuition. Now we come to something what Bikram was asking, and it has a name. It has a very special name that you might have encountered called a similarity transformation. Similarity transformation. So in similarity transformation, you are taught that if you have a matrix T, then you can always have a matrix A inverse here and A here that transform this matrix to another matrix. If you choose your A and A inverse cleverly, so certain choice of A can make your T, the new matrix, diagonal. It can make them diagonal. So the fundamental idea is, what I want to teach you now is the similarity transformation that you actually do using the concept of eigenvector and eigenvalues is actually nothing but it is related to the idea of change of basis. So similarity transformation is nothing but, in short, you are actually changing the basis. Now we will look at this very closely. Okay, so for that, let's start with what we already know. Remember that there was this kind of stuff, u I prime, the new basis, is equals to some matrix aij and the old basis, from which you derive that the old coordinates are transpose of the above matrix, which I'm writing it in a funny way, which is this. So this is just transpose of the above matrix, and x prime I. Okay. Now let me write them in short. In short, it is u equals u prime equals au, and x equals to a tilde x prime. So where a tilde is another representation for A transpose. Many books they use it. If you want to write A transpose, you can write A transpose. It doesn't matter. It's just the same thing. Now, what I want to convey here is, consider you have a matrix T. So consider a matrix T, and consider you are in so there are two vector spaces. This is one vector space, this is another vector space. What we will do is, we will work in the vector space with the same dimension. If we are in R3, then we want to be in R3 here also. So we are in the same vector space. Now, so instead of making two vector space, I can just make one big vector space of R3, and I can talk about the following thing. I can say that there exists a matrix T which acts on a vector X which belongs to R3. This matrix takes you to another vector Y in R3. So there is a matrix T in R3 that takes you from one vector X in R3 to another vector Y in R3. Okay. Now this matrix T, we have to find it is defined in which basis. That's very interesting. Okay. So if you look at this idea, the how X and Y are defined, from here it is clear that T is defined in old matrix, in old basis U. Yes. Now if I change the basis, if I start writing Y prime is equals to some matrix which acts on X prime, then from here it is clear that since X prime is a vector that can be written in the new basis U prime, Y prime is a vector that can be written in the new basis, that means the T prime here is defined in the new basis UI prime. Now the question is how T and T prime are related when I change the basis and I go to different basis. So that is, if you have a particular matrix in one basis, and how does the matrix is gonna look in another basis and how they are related. So T is a matrix in old basis U, T prime is a matrix in the new basis U prime, and I'm saying that there is a relation between T and T prime, that the old matrix operator in old basis is related to the new matrix operator in the new basis. Why they are related is because of the simple reason, when you change the basis, there is a matrix that tells you how the vectors also transform. So there is a matrix that transforms the basis, there is a matrix that transforms the coordinates of the vector or the vector. That means these matrices should be somehow responsible in transformation of the matrix T from one representation to another representation. Let's do it in a very simple way. So the idea is very simple and it is the following. Now if I am able to, we know there is a, for example, Y belongs to R3 and Y can be written in old basis U, and Y prime also belongs to R3, the same vector but with different coordinates. So when I'm writing Y prime, you should always think of the same vector but with different coordinates. So these notations are quite confusing, but anyways. And this is in UI prime. That means I can write Y prime. So what is the new one? A new one is my Y prime. So new stays here and the old is here, and then there is a matrix, this one. Here what I have written. So you see this one. So they have used, I have used capital A transpose, so better I use capital A. Okay, just to remove any confusion. So you have Y prime and Y and capital A with a tilde. I used this notation. Similarly, your X was also in R3, then X was defined in the old basis UIs, and your X prime is also the same vector in R3 but with different coordinates and hence different basis. That means I can write x is equals to a tilde x prime. Okay, this is clear. That means I can write y prime is a tilde inverse y. I can write x prime as a tilde inverse x. Okay, so this is a small notation. But what is the main idea? The main idea was the following, that there was a matrix T that actually took you from x to y. This is the main idea. So there exists a matrix that took you from one matrix to another matrix. So when I write y and y prime, they represent the same matrix y, but with different coordinates because the bases are different. When I write x and x prime, I'm sorry for the notation, but what to do? When I write x and x prime, they represent the same vector x in R3, but with different coordinates depending on what basis you choose to represent them. Okay, so I hope this is clear. So when you have y, now you can do a very interesting thing. You can start with y prime is equals a tilde inverse y, and you know that y is nothing but t of x. So the t is the old t and y is the old y, x is the old y, all can be written in terms of old basis ui. That implies y in the new basis is equals to a inverse t. Well, we can write x in terms of the new x, right? So x, remember what was x? X is equals to a tilde x prime. So since this relation is known, so what I can do is I can write the x here as a tilde x prime. That implies I have a new matrix T prime that takes you from x prime to y prime in the new basis, and the T prime is related to T in such a way. So the similarity transform that you actually do is equivalent to taking a matrix operator that was represented in one basis to another matrix operator represented in another basis. I mean, the matrix operator is the same matrix, it does the same operations, but only the representation is different because the basis that you use for representation has changed. Any doubt here?
No.
No. So it would be nice if I can come up with an example that actually makes the whole idea okay. Let's try an example. Okay, so consider you have a B basis, and let this be a standard basis in R3, and we know that they are represented as 1 0 0 0 1 0. I can write it in column form, but many books they write it like this. It's the same thing, so it saves the space, the vertical space. Let this be a basis B, and consider there is a matrix AB, which is the transformation matrix, or instead of AB I should write, I should write TB, or maybe T. No, it's better TB. So TB is equal to T. That is the old matrix written in B basis, and let it look like this: 1 2 -1 0 -1 0 1 0 7. So this is an operator which, when x on any element x in R3, so when TB x on any element x in R3, it takes you to another element y in R3. Now I ask you, if I define a new basis C, again we are in R3, but the basis is gonna change, say 1 0 0, comma 1 1 0, comma 1 1 1. So if I have such kind of basis, then can I find T prime, or how TC or T prime is gonna look? And what is the behavior of TC? Now TC takes one vector x prime in R3 represented in which can be expanded in the basis C to another vector y prime in R3 which can be also represented in the basis C. Okay, this is the fundamental idea. Now what to do? The idea is that we need to find this A matrix. Here what we have used? We have used A transpose. So first we need to find matrix A and then transpose it and then use it here. So how to find the matrix A? So remember that the matrix A told you how the basis in new is related to the basis in old. That means remember this U prime is equals to AU. So U prime is actually our C because C is the new basis. So U prime was actually C. This is our new basis and this is our old basis. So we need to find a matrix A that takes you from new basis to old basis. Okay, so let me represent B as basis B1, B2, B3. Okay, let's do it in a new page because I need to do a lot of calculation. So the basis B, which was in R3, contained elements 1 0 0, 0 1 0 and 0 0 1, and let me represent them as B1, B2, B3. Now the C basis, which is the new, so let me write this as the old. By old you should remember U, and by new you should remember U prime, and C was 1 0 0, 1 1 0, 1 1 1, and let me represent them as C1, C2, C3. Okay, so can I write C1? C1 looks equals to B1. C2 looks as if it is B1 plus B2, and C3 looks like B1 plus B2 plus B3. So what I have done, I have actually written U prime in some matrix A into U. What is the matrix A? The matrix A is 1 0 0, 1 1 0, 1 1 1, which can be easily derived if you look at this relation carefully. What we need to do? We need to do A transpose, which is 1 0 0, 1 1 0, 1 1 1. This will help us. So now what was our matrix? TB can be transformed to TC if you just use A tilde inverse and A tilde here, where A tilde is calculated here. Okay, now if you do this, which is up to you, you will find that the new matrix or the same or the operator T, matrix operator T in the new basis looks like 1 4 3, minus 1, minus 2, minus 9, 1, 1, 8. So for convenience, let me tell you that A transpose or A tilde, whatever turns out to be, was this. And I can also give you what the inverse is going to look like so that it's easy for you. It is 1, minus 1, 1, 0, 1, minus 1, and 0, 0, 1. So I think now what you can do is you can use A tilde and A tilde inverse and use this formula, and you can find TC. So you look at this carefully. This is nothing but a similarity transformation, right? We all remember what similarity transformation is. Okay. So what did we learn from this exercise is that what you actually do similarity transformation is nothing but you are actually going from one basis to another basis, and to go from one basis to another basis, the matrix A helps you. To go from one basis to another basis means you're going from one coordinate to another coordinate, so the matrix A transpose or A tilde helps you. And to go from one coordinate to another coordinate and one basis to another basis means that the matrix operator, which was defined in one basis, and the matrix operator, which was defined in another basis, you're going from one matrix operator in one basis to another matrix operator in another basis, and which is quite obvious that it should be related to the transformation matrix A. So the transformation matrix A helps you to go from one basis to another basis. The transformation matrix A tilde helps you go from one coordinate to another coordinate, and hence the transformation matrix A helps you in going from the matrix operator in one basis to the matrix operator in another basis. So the class ends here. I think we don't need to do linear algebra anymore. I have taught you many things in between in a simple way, and you can look up to some linear algebra textbook and read it yourself, and if you think you have not understood something, we can discuss. From now I will go forward with groups, and there are certain things that I need to teach you in groups, and then we can go to Lie group, Lie algebra. I think within 5 to 6 classes we'll finish. So we end our class here. Do you have any doubts?
No.
Okay, so we meet, I don't know when, I'll let you know. Okay, so just record these videos and keep uploading, and I need someone to actually trim, crop the videos. How to do it? So Ilham, when you're watching the videos again, can you edit the videos? Like sometimes when you have too much background noise, or sometimes when I'm saying some unnecessary things that can be cut, can you do those trimming work because you are watching the videos again?
I can try to see if I can.
I mean, do you have any experience with these kind of softwares? If not, then fine.
I haven't done it before, but I can try.
Hello.
Hello. Can't you hear me?
And now, yes.
Can you hear me?
Yeah. Tell.
I thought I haven't done this work before, but I can try.
Okay. Then leave it. You just record the lectures, keep it, and Bikram is recording in his drive, and you record, keep these videos with you and upload it in a drive, and maybe me and Bikram will tackle this. Okay. So the next class maybe at night, but I'm not sure. Okay.
Okay.
Goodbye.
Okay.